So let me now continue with the amplifiers. Please remember, one of the main feature of analog design is an amplifier design. That is our major workhorse. So we want to understand everything what an amplifier can do or how to get to that spec. Okay. So we have looked into common source, common gate, source followers, normal single stage amplifier. We looked into cascodes. We also have some interesting features about the how analog circuits are important in the current scenario. My first few lectures on PPT. So this is all that we have so far covered. Today we start with more details on that. The first thing we would like to know what kind of loads one should use. All this time I was using a resistive load, which is essentially a actual resistor. The problem with actual resistor in a circuit, not that we will never put that, but essentially we avoid it, as I discussed earlier sometime, that the sheet resistance available for normal CMOS design, CMOS technology is not very high. So we said that the load resistance of typically 40k will be required, and for that values 10 to 40k, the aspect ratio is so high that it will be very difficult to put more than few resistors on chip. That means it will take more area for resistor than the transistors. So we said okay, we will not like to use resistors as made out of normal semiconductor. Please do not think that I will never use it, I will have to use somewhere, I will, okay, but normally I will avoid. So replacing a resistor by a transistor itself is called active load, and therefore we are saying device is now replaced, resistor is now replaced by the device which acts like a resistor. These are called active loads because transistor is an active device. So one of the most commonly used load in almost all analog and also in digital is called diode connected load. Okay. Now what is this diode connection is I think we have done many times earlier, so I will not explain why name diode, but think of it, there must be something in it to call diode. In this case for N channel the gate is, or for P channel, gate is connected to the drain, okay, permanently, okay. And then if you evaluate the resistance seen, you can see from your IDS VDS characteristics, if the device remains in saturation throughout, in that case for a given VGS, which is what is VGS here, VDD minus Vs, VGS is how much, because VG is connected to drain, so VGS is VDD minus Vs, and if that remains always smaller than VDS or equal to VDS, the device will permanently remain in saturation, and if it remains, this resistance of the characteristic shown here, which has a very large R because of the slope is very low, this can act like a resistor. Okay. The example whatever I said is given in the formulation, VDS is VGS plus VDS, VGD. Since VGD is made 0, VDS is always equal to VGS, and therefore VGS minus VT is always less than VDS, and therefore device is permanently in saturation. Okay. And the characteristics, current characteristics can be written as beta by 2 VGS minus VT square, assuming lambda small. You wish to put lambda, you can, though you may say if the lambda is 0 then that should show infinite, but assume the value is whatever derivable, and this acts therefore acts like a constant current source. So sometimes it is also called current source loads. The diode connected loads are also sometimes called current source loads, okay, because this is a current source, it is only a function of given VGS and therefore it is constant current source. Now I will show you what is important for us a good current source, that it should have a large parallel resistance to the current source, as phi is, that is the better one. So we will evaluate for this case what is the impedance seen by this device as a load, and if that is essentially is the feature how good is diode connected load will be. Okay. Is that okay for those who are written down now? So if I wish to figure out R0, I put an equivalent circuit as I did earlier. Please remember we say VG and VD are connected, gate to drain, so drain to gate, gate to drain is connected, okay. You have V1 across gate to source, GM V1 is the current source, GMB VBS is the current source. Due to the body back bias, R0 is resistance, and this drain is also grounded now for AC, for VDD side. Now if you see, and then I apply a source Vx and find a current there, and Vx by X will be R0. Essentially if we rewrite the current now, Ix which is shown here in this direction, you can choose any direction, do not worry, sign should be taken care otherwise. Since this was a Vx source I applied, current leaving the source I used as plus Ix going up, okay. So essentially this current and this current must balance, because at this node the net voltage net current must sum to 0, okay. At source node this current and sum of these current must equal to 0. So if I rewrite Ix is equal to Gm plus GMB Vx plus Vx by R0, and then I write Ix is Gm1 upon R0 Vx, I get, and if I say R0 is very large compared to 1 upon Gm's, Ro which is the resistance seen here for the device top device, that becomes 1 upon Gm plus GMB. In case GMB is also not given to you, many times I may say there is no back gate bias, and in that case it is only 1 upon Gm. Please remember there is R0 is sitting there, essentially R0 is across 1 upon Gm, and whichever is smaller will take care, since 1 upon Gm will be smaller compared to R0. So one can say typically diode connected loads gives you a resistance of 1 upon Gm and not R0 as we thought. That is the issue which I wanted to raise, okay. Is that point clear? The resistance seen by the lower device as a load is just 1 upon Gm under diode connections. Is that correct? Is that clear? Now this is an issue, whether this is good enough or not is what designers should know. If your GMs are very low, yes, this RO can be as high as possible. Alternatively, when GMs are low, when GMs will be low? When is the GM low for a normal device? Either the current is flowing is low, okay, which may be good in at times for what purpose? Low power, okay, current is reduced, or the W by L is smaller. So the smallest size transistors if you use, your resistance can be built. Please remember, normally the channel length which you can create is normally a technology parameter, okay. To reduce W by L, all that you say, do not use the minimum channels, use multiple channel lengths. That is, if you are working on 90 nanometers, typical channel length is around 60 nanometers. So you put 120 nanometers as length, instead of L put instead of 60 you put 120 there, that you can always, you cannot go below 60, you can always, so W cannot be go below 60. So do not decrease W, but increase the lengths whenever you need. This is also true in the case of lambda, when we say if you reduce lambda is lambda dash by L and you want to reduce lambda, that is the bias parameter, then what do? Increase lengths as much as possible. So larger the length, smaller is lambda and better is the current source you get. So that is similar feature is also appearing in this analysis. Is that correct? So longer length device is good for good analog blocks, okay. However, what is the problem? Larger the length you put, the size of transistor will enhance, W into 2L, which means area penalty you are paying. Something else I did not say, you will also figure it out, the capacitance will vary because of the area variations. So somewhere bandwidth may also get affected. Okay, how much we will see when we go to frequency response. So there are issues, so it is not that you just push it or just reduce it. For a given design you must choose what else you should use, what is possibility available, so otherwise do not use diode connected loads if that is hurting you so much. Okay, is that clear? Okay. If you look at the gain of an amplifier which has this diode connected, same thing which I stated is given here, do not rewrite. I already said GM is proportional to W by L and IDS root of IDS, and that is what I say increase lengths. Okay. The gain is GM1 RO, if RO is this. Of course it is also shunted by RO1 of the driver. Okay. Since if RO2 is smaller than RO1, then it is only RO2, if not then you have to figure it out how much it should be, parallel curve. So put parallel and whichever terms is smaller will take care. Okay. So if I substitute this GM1 into this figure, I get on and roughly I will say AV0 is W by L by 1 by W by L2 divided by 1 plus eta. If eta you do not want to put it 0, you may also use eta 0 if many cases. So what is this kind of amplifier is suggesting? That but just make a ratio of W by L of the load transistor to the W by L of the driver transistor, and you can adjust your gain without any other parameter in question. So if you are looking for something constant or variable which should not affect your AV0, then this is an ideal situation. Just sizing, and please remember individual size is not relevant, the ratio is relevant. So you can adjust individual sizes to suit something else, but still make a ratio of required current gain, voltage gains. That is the strength of diode connected amplifiers, diode connected loads for an amplifier. So choice is not that you should use or you should not use, choice is when to use, you should be aware of. Is that point clear why I showed you diode connected loads? Because one wants to know that just by adjusting the ratio I have a control on the gain itself. Okay. Is that, am I clear of what I am saying? So this is something very interesting in designs, because if I do not have to worry too much about VTs, I do not worry about VDD, if everything is, as long as device in saturation, thank you very much, the ratio will take care of my gains. And remember the ratio is independent of what? Temperature, environment, any other things, and therefore we say just by design parameter I am controlling the gain. And which is the design parameter? Which is on the plan of the wafer, or which is the surface area which I am controlling, nothing to do with in the wafer inside. Okay, that is something great happens. So this is, it is inaccurate because we have assumed few things, but to a great extent this is reasonable assumptions. So what is the way I will say when I say I want to design an amplifier of a gain of 1000, I will never say 1000, I will say the minimum gain expected is 1000. So this adjustment is still within your hand, you say okay, as long as it is not lower than 1000 and other parameters you wish to control, you have right to control. Normally gains are never specified 976 kind of thing, okay, there is nothing such things. Okay. So as I say, we can also use amplifiers, other loads also. Okay, the other loads could be what I said other day, just by putting an N-channel transistor and biasing it, that means if this transistor is biased heavily by me such that VGS is minus VT is always greater than VDS, so transistor will remain in non-saturation, so linear mode resistance, smaller resistance, and the value, how will I adjust that value? By W by L's. So again by using a W by L and keeping VGS minus VT larger than VDS for the load device, I can control my smaller value of resistances. Okay, okay, so next we move to the most important amplifier which is almost used, I won't say excluding to other 3, but most times we will use this amplifier for all amplification purpose in analog is a differential amplifier. Now this word is slightly worrisome to me. There are words in the books called difference amplifier, there are words is called fully differential amplifiers, okay. So we should be slightly worried about these statements. Right now the difference amplifier and differential amplifier here is the same. So if I say diffam or difference amplifier or differential amplifier, I mean the same, but later on in some design I will say it is a fully differential system. So I will define what I meant then. Till then assume that difference amplifier, differential amplifier or a diffamp is same. Now what is the problem in common source, common gate or common drain amplifier? One of the major issue of which we did not discuss very often in earlier designs is we know that their properties strongly depend on the Q point, where do you put your biasing, okay. Now biasing seems to be trivial to many, just apply bias and you get it, okay, it does not happen so easily. For example, if I put a V bias in series to the signal, yeah, it is going to bias this transistor, keep it wherever you wish, series in non-saturated, saturated, whichever way, and this should work, but this is not working the way we thought it should, okay. Since gain of an amplifier is constant only and only if Gm and R zeros are constant. However, the value of V bias and the signal overriding on that bias, the amplitude of this, where do you bias and how much is the signal sitting on this, on a real characteristics may push you device from different R0 values and therefore sometimes different Gm values, okay, which essentially means both the parameters of Gm and R0 are strong functions of not only V bias but what is the amplitude of the signal and where it is biased, okay. So our assumption that the gain is constant is not very true because it is now a function of input, which is never we wanted, because if that happens the gains will be different at different input sides, okay. Particularly if this may happen when the gains are extremely high, swings are too high, and that time these assumptions are not very good and therefore we may worry about how to get good biasing. What is the condition I am saying? That biasing should not influence the outputs, is that clear? That is what ideally I would like, so that I get good current voltage gains. Yes, if we use constant current biasing, maybe this issue can be addressed. A typical biasing system can be something like this. This is say I bias, which is flowing through this transistor and its drain is connected to the gate like a diode essentially, but the same gate is connected to the actual amplifier which you want to bias, okay. This is the precursor of the mirror, okay, that is the idea behind mirrors, okay. Now what we do is, the way we kept these two transistors are identical, okay, their gates are common, their sources are common, so what is equal for both of them? VGS is equal to VGS M, call it say M1, so VGS for M1 is same as VGS for M2. Now you want to put input signal, so you must put through Vin. Now you have to put this value, why you have to put this C? Because you have to isolate AC from DC. So I put a series resistance to the source, a series capacitance to the source which is CS. However, if this capacitance is only left there, it is like an impedance at certain frequencies. What is my idea is that for a DC at least it should pass everything, all frequencies should it pass. So instead of just CS, I must convert it into some kind of a high pass filter whose cutoff is very close to 0, little higher than DC, but so where should I put a resistor? And since there is no gate currents, what does that mean? Any resistance will not change any drops across because there is no current in the gate side, is that clear? Because gate is isolated from by insulations. So if I use this circuit and convert it slightly modified way. Okay. So what he said, and I agreed with him, that yeah, I can use current biasing and I can have independent of my actual transistor. I put left side my bias circuit. That is what every analog designers will find, there will be biasing block. Okay. Of course that would learn separately, how to create references both for current references as well as voltage references, which will make this constant. Okay. So that is another part which will look learn. So with that circuit, then this whole circuit will be called biasing circuit. Okay. Now I am showing you very carefully, this is now required in what we call in normal digital hardware, which is called DC to DC converters using constant biasing sources or constant current sources. This is called biasing module. Now you have to create 1 volt, 1.2 volt, 1.5, 3, 5 many voltages you need on the digital these days. So this is one of the way this can be created, change the sizes and you have different values. Okay. So I said okay, I put a larger resistance this, then this is essentially high pass filter and this has a cutoff frequency upon 2 pi r large Cs, and we want this to be as low as possible, good high pass filter. This means R and C should be very high. Now what is the problem with R and C high? Both are functions of lengths and widths. Okay. When you make on a silicon, they will be functions of W and Ls, whatever size you keep there for them. Larger means larger area you are picking up anyway. So if you can do this, this is a good way of doing it, but it has the feature that it actually increases the it requires additional area to implement. This will do your job guaranteed. Please remember, this is the scheme which we do employ in an RF amplifier. This course is not going to talk of RF systems, but if it does, if I had to, then I say okay, this is one of the very common biasing techniques in the case of RF. Okay. So if you are designing a power amplifier or a low noise amplifier in RF range, probably you may look back and see this was one method I used there in those designs. Okay, so please remember, in this scheme I bias is going to decide the GM of M2 or whatever name I M1, and therefore it is independent of V bias. Whatever comes here I am not worried, it is only I which is going to decide the GM. So I have avoided that V bias dependence by making a constant current source there. ओके ये भी करने की ज़रूरत नहीं, इससे अच्छा बाइसिंग जो है, even if variations occur and if it doesn't still change anything, then why should we worry so much about it? Okay, and that's what exactly the differential amplifier does. Okay, why this was a precursor sheets to show you why differential amplifiers became, apart from many other advantages of differential which is making so important. One of the reason was that the biasing became very trivial in the case of difference amplifier, because even if it is not constant, it takes care of it. Okay, and that is some fun part in that. The differential amplifier gains are normally very stable gains. Okay, and that is why we prefer differential amplifiers. Apart from many other features which we shall now discuss, that differential amplifier is far superior in many characteristics over single stage amplifiers. But then why these single stage amplifiers are sitting at all? Okay, this is an issue we should answer. Okay. So I just want to tell you very clearly, a differential amplifier is a better solution to this biasing problem compared to what I showed for single stage. Let us say I have an input Vi. Okay, what is the differential amplifier? You have two transistors M1 and M2, which sources are connected and given a common bias current source. Okay. Now there is also case the same different loads kind current sources I create, I can use one of them to create this right now. Right now my assumption is I bias is ideal, but in real life I bias may not be ideal source, so what it may give some resistance, so what it will affect us. Okay, but as of now for simplicity we start with thing, it's good thing. Then we have a load RD, they can be RD1 and RD2 and they can be same. So it is not a compulsion that they should have same loads. Okay, so we say the GM of both these transistors are decided by, this is sometimes called bias current or tail currents. Some book call it tail, some book will call bias. So whichever books or book or none, whichever you are take it, either it is called tail current or it is called bias current. Okay. So since this only decides the GM in this, an interesting outcome of this difference is that the difference of output voltage is now only proportional to the difference of input voltage. I repeat, the AC part, as if I show you VO1 minus VO2 is only decided by VI1 minus VI2 and nothing else. Okay. So there is no way, if this changes, still it will give the difference of that. Okay. What will happen if there is this, both will get affected and in difference they may not be available because difference will get cancelled out. This is the idea. So the first problem of bias variations or bias dependent variations at the output can be eliminated if you have, if variation occurs it should occur together and the difference will cancel it out. So this was the one reason, as I repeatedly saying, this is not the only reason, this was one such reason why DFAM was preferred, because they say okay, these bias issues are partly taken care by. Okay. So even if this is not doesn't matter, I am not very much worried on that. Of course if it changes so much that device goes from saturation to not, then I am worried, otherwise swings are not of my interest. Okay. The another part which all of you are aware for this DFAM of course is, since I said so, difference, anything which, assuming that the any noise is universal and whatever additional noise voltage appears here will also appear here, then Vi1 plus V noise, Vi2 plus V noise, and if I take a difference I leave the noise part anyway. So anything, the word now which will later come is common mode, which is common to both, will get anyway eliminated at the output. So the major reason why DFAM was used, that it allows you to remove noise, common mode noise from the any circuit. The assumption of course is, in a small area DFAMs the noise pickups are similar. Before we go, maybe I have another few things. Another interesting feature, as I say, first was the bias, the second was the noise, common mode noise as we called. There was something third which common mode systems which rejection it occurs. The word is, that is why there is a famous term we use for DFAMs as common mode rejection ratio, okay, CMRR. That exactly is the measure for that, how much rejection it will do. Ideally it should be infinite, it should common mode gain should be zeros, okay, preferably, but it will not be. So there will be some large ratio may come which is good enough to say effect of that is very small. Okay. Okay, so the third and the very important feature which is that okay, which is not, I think I did not think earlier but just now I remembered, particularly this is for the people who are working on digital or mixed signals. There is a huge issue right now going on. Where is your digital course right now, VLSI design? There are issues, or maybe system design course is in next semester, isn't it? Okay. So one of the issue there we figured out, you have one interconnect, okay, and a signal is entering from here. This is your out through a interconnect. This is a signaling problem which is very trivial, which very important, and let us say there is another interconnect which is across, which is called, and this in our terminology there is called aggressor cell or aggressor cell interconnect. Now if you have two such interconnect lines close by, not necessarily orthogonal but even parallel, there is a capacitance which is associated between the two lines. Okay. Now since there is a capacitance associated with two lines, so if whatever signal you are going to put, depending on this coupling it goes, the voltage here may actually be something like this or sometimes like this. Okay. So your data transmission will be actually impaired heavily, and if there are more than two aggressor lines it may actually hit you worst. Okay. Further there is also an issue if the data is flowing in this direction or flowing in this direction in aggressor, that may also change the output patterns. Ideally I do not want this to influence. So what I say it, okay, if you have an aggressor here, I have another interconnect line, I have same signals going to both this, and the output I will take the difference of the output as well. Is that clear? So now whatever change is occurring between these two lines, it will get eliminated because of the difference outputs with the difference inputs. Okay. So in aggressor cell effects can be nullified equivalently by putting another parallel another line for it. Okay. Penalty is huge area you put it actually, but signal system people will tell you it is better to have larger area chip than not working chip. Okay. So this is an issue which there we solve by different ways. This is a crosstalk issue. There are a number of ways we tried, and this also increases the power dissipation. So for low power this is one of the issue, how to reduce the power actually. So there are issues which digital people are looking into, and there also we will prefer difference outputs or difference inputs, two indifference input. So diffam, it is not really connected to diffam word, but trying to show you that where these different schemes actually are useful. Okay. Is that point clear? So please take it, these are the issues which are cross connected to digital. Okay, so as I said, diffam has advantage that it will use common mode rejections if possible, and it will solve much of the biasing issue. Okay. In addition to that, if it does something more, okay, that is a bonus for me. If it does not do it, at least gives gain of a common one single stage is fair enough, but if it does even better, which I think I will, then I have got much more value out of the same system. Okay. And that is why diffams are most popular amplifiers. Before we go to the small signal analysis, it is intuitively proper, it is intuitively one must think about the large signal behavior. Large signal means only DC values are used there, ACs are small, you can add to that if you wish, but basically we are looking for DC analysis. Okay, so let us say you have a differential amplifier with two transistors M1 and M2 which is biased by ISS. This word I changed from I bias to ISS because this is what Razavi says, so I thought at least if you go and read Razavi once at least, you should not feel very suddenly different. Okay, so first I wrote bias, then I realized I opened the book of Razavi, he said what I tell currently says ISS, so I changed to ISS. Okay, does not matter, you can use any number. Vn1 and Vn2 are the inputs, and the most important worry and most important point which we want to discuss through this is this point P, which is common point for sources of both M1 and M2. Now figure it out this, if per se this voltage at P changes, VGS of this and VGS of this may not be same, is that correct? But does that really affects you? If it does not, or does it change at all? Okay. We will like to see by this system whether the P point is stable, that is why this large signal analysis. Okay. What is the VO1 will be VDD minus RDS1 times RD1, VO2 will be VDD minus drop across RD2. I subtract VO1 minus, this is difference output voltage, VO1 minus VO2, and if I subtract here it is IDS2 minus IDS1 RD1. or IDS2 minus ID1 into RD, assuming RDs are same. Further, if you look at the input side, this is VGS. Okay. So we say V in 1 minus V in 2, what is essentially the value V in 1 is equal to VGS plus drop across current source if any, is that correct? But that is common for both sides, so I do not take care. Otherwise say V in 1 minus V in 2 is subtraction of VGS1 minus VGS2. For the simplicity, lambda is taken 0 for all analysis till stated otherwise. Okay. Is that okay? Please remember, lambda can be taken care. All that will happen is, nonlinear terms will start occurring in under roots and squares, and then analytical solutions will not be very easy to understand. We are not really designing on them, what we are using it to explain something, and since lambda is anyway 0.01 or 0.04 or 5 kind of things, it will not drastically change the physics anyway. Okay. However, physically please do not leave lambda as 0 if you are calculating R0, because otherwise that R0 may become infinite, gains will infinite. So do not think that I am leaving lambda, but for explanation of voltages I do not believe it is very much important. Is that okay? Okay. Is that okay? Expressions we wrote V in 1 minus V in 2 is VGS1 minus VGS2, and VO1 minus VO2 is IDS2 minus IDS1 times RD if RD1 equal to RD2 equal to RD. Is that okay everyone? So now we write the drain current as beta by 2 VGS minus VT. So we can also write VGS as under root of 2 IDS by beta. Also we have used alpha equal to 1 in all this analysis. As I say, unless stated otherwise, use alpha 1 lambda 0, otherwise if given, or even eta equal to 0 unless stated otherwise. Okay. So VGS is for a large signal, these do not matter, so we do not add that much. Small signal, yes, I may add all those terms because small signal they will actually affect it. So VGS is 2 IDS by beta plus VT. So if I want to write V in 1 minus V in 2, then it is VGS plus VT, VGS VT minus this, which is essentially, I write two terms for IDS V in 1 and V in 2, which is equal to 2 IDS 1 beta minus 2 IDS 2 by beta. To get the point, IDS 1 and IDS 2 appeared in output, so I now replaced input also in terms of IDS 1 and IDS 2. Is that point clear why I did this? The output was a function of IDS 1, IDS 2, so I say okay, input is also in a way explainable through IDS 1 and IDS 2. Okay. One important feature of FEM is, which is very important, if you write down, you first write down only up to this and then I will come back and show figure and come back to this. Is that okay? Is that this much you are written above? Okay. So if we see the figure here, the drain current of M1 and drain current of M2 can only sink through the current source, okay, which means whatever value of IDS1 and IDS2, their sum should be always equal to the ISS. So this is the major feature of a DFAM. It may happen this may be larger, this may be smaller, or this may be larger, this may be smaller, or they may be equal. In any case, the sum total will be always equal to ISS, and that is the feature of a DFAM. Okay. So since for all cases IDS1 equal to IDS1 plus IDSS, we now rewrite V in 1 minus V into square is square of this minus 2 times this, multiply if you take it 4 by beta IDS1 IDS2. Then we say IDS1 plus IDS2 is ISS, So 2 by beta ISS minus 4 by beta under root of IDS1 into IDS2. ये थोड़ा मैथमेटिक्स सब जोक के लिए हो रहा है, but just we want to show at the end of the day what should be the limit of V in 1 minus V in 2, corresponding to which IDS1 IDS2 should be available to us. Before I go ahead, maybe I physically still I may tell you what I am trying to tell you, so that this whole expression which I derive will be aware. Is that okay? You have written down these 3 lines? Okay. What I am trying to say you is the difference of these two currents IDS1 and IDS2 is a function of difference in V in 1 and V in 2, but if say V in 1 is equal to V in 2, then we believe that IDS1 minus IDS2 must be 0, they must be equal, okay. And if that occurs, we can say each current is half half, because IDS1 must be equal to IDS2. Equal to ISS means each arm must flow. So if the inputs are same, we want to see, or difference of input is 0, then each arm will get 50% of IS. That is what we want to prove, which is anyway visible from here, but mathematically maybe I will show you. Yeah, it does come finally after huge equation solving. So we say, expressing that, beta by 2 V in 1 minus V 2 minus ISS is minus 2 IDS1 IDS2 under root of that. However, mathematically IDS1 plus IDS2 square minus IDS1 minus IDS2 square, यदि दोनों को expand करेंगे तो ये 4 IDS1 IDS2 आता है, इसके 2 माइनस उसके 2, तो 4, okay. So 4 IDS1 IDS2 is nothing but subtraction of these two, but what is this term? ISS square, okay. So we write ISS square minus IDS1 minus IDS2 square is 2 under root IDS ID2 whole square. Therefore this term IDS1 minus IDS square is ISS square minus 2 IDS square, but this term is how much from here? Beta by 2 V in 1 minus V into square minus ISS square, इस term को यहाँ लिख दिया, okay. I use this term in substituting here, okay. 2 IDS1 IDS2 ऊपर से beta minus V in 1 यहाँ term ले आए, expand करते गए. Yeah, that's what I was also thinking why I am doing this. I want to show that V in 1 minus V in 2 plus minus हो सकता है. So up to what value of V in 1 minus V in 2, which currents both will flow or one of them will flow, from onwards where the other current will down. So I say if IDS2 start going down or IDS1 start going down or IDS1 becomes maximum, that figure I want to draw, okay. Is that okay? So I want to plot IDS2 IDS1 against delta V in, which can be plus or minus. Why minus? Because if V in 1 is higher or lower than V in 2, it can be plus minus. Physically I already said, if V in 1 minus, okay, you have written down this expression, you write down, I will come back to maths physics again, very trivial thing I am rewriting, but I want to show mathematically derivable things which you can otherwise also understand. Okay, so what I was saying you is this figure, if you see again, basically what I am saying, if VGS1 is or V in 1 is much larger than V in 2, this will draw larger current, is that correct? Larger this current means smaller this current, because ISS is fixed. So if this draws more current, the other will go down. If this is larger, that is delta V in is minus now, difference. If this is larger, this will draw larger current, this will draw smaller current. After a while, when this transistor does not have enough PT support, all the current will either flow here or flow here, is that correct? So at certain value of delta V in, beyond that only one of the transistor will remain turn on, and because of that all of ISS will flow through M1 or M2. Is that clear to you? This is what physically visible. Okay. So okay, after all that equation you can rewrite. This becomes IDS1 minus IDS2 is beta by 2 V in 1 minus V into square 4 ISS by beta minus V in 1 minus V into square, and V in 1 minus V in 2 is essentially delta V in, difference of the two. So if difference of the two V in 1 is equal to V in 2, IDS1 minus IDS2 is 0. Is that, first write the expression which I said physically is visible now. If V in 1 is equal to V in 2, that is delta V in is 0, IDS1 is equal to IDS2, but IDS1 plus IDS2 is ISS, each arm will take 50% of the ISS. Okay. So if both inputs are same, then 50% current. Okay. In case this is larger, delta V in is positive, this term will subtract from this, and if you keep increasing plus delta V in, after a while this term will start mathematically reducing, and you can say, or rather difference, so IDS1 will almost become ISS, this value is typically ISS. Okay. This was therefore ISS by 2. So as V in starts increase, delta V in starts increasing, IDS2 start falling and IDS1 start increasing, because that is the expression is asking me. As I increase bit beyond, the other transistor is if turns off and all of the current goes to IDS1. By same logic, if I do the opposite side, symmetry tells IDS2 will reach ISS and IDS1 will become 0. This fact that differential amplifier essentially allows current switching from one arm to the other when the input changes beyond delta V in of this value, 2 ISS by beta, then we may say it is either drawn current here or drawn current. So as long as you remain between these ranges, you have some sort of IDS1 and IDS2 available, which is where DFAM should work. Is that clear to you? So what is the signal available to you to move out is only 2 delta V in, is that correct? But the catchword there is, if you have an input V in between 2, V in 1 minus V in 2, if I increase 1, by the same amount if I decrease the second, then the change is double. Is that point clear? If I say V in 1 plus delta V in, so the V in 2 minus delta V in, is that clear? So the difference is now essentially 2 delta V in, so you switch over from one to the other. Is that point clear? That is essentially the feature of a DFAM. Is that point clear? So why I showed you all the maths which Radhavi did is to prove this point that device switches over from, and in these two ranges device is operating for, as a both device are operating, and therefore certain amount of difference outputs can be obtained. Is that clear? Now this interesting understanding is only to make point clear. It is not solution for anything. This is just to say what happens in DFAM. Okay. So this is called principle of DFAM operation. Okay. This only tells this, that switchover occurs from one to the other. So now we will like to prove later that if this VP point shifts, or does it shift? If shifts, does it troubles us, and if it does not, why it does not shift? Okay. If it does not shift, all this analysis will be valid, because VGS I will say is same all the time. This ISS by it was 2 equal to, both sides will go only if VGS1 is equal to VGS2. Is that clear? Now this fact S remaining same, will IDS1 IDS2 will also remain same. If not, then I have to figure out, because VGS changes, IDS1 IDS2 will vary. but I feel I do not think IDS1 because VO1 VO2 remain constant we observed. So I want to say Vp does not change. Okay. Now to prove this point and to do one method of analyzing an DFAM, why we are looking so much in DFAM? Please remember differential amplifier is not independently used for all application, most of the time it will be part of first input stage of op-amp, okay, that is the input stage of an op-amp. Okay. So we will see that is the op-amp part. So we will see output amplifiers separately, we will see shifter I already said can be done, and if I see DFAM then I know now I can control my op-amp characteristic because I know all three of them. That is the trick I am using to arrive. At the end of the day my interest is in designing a op-amp. If I can design an op-amp for a given spec, I have done almost 90% of analog efforts. 90% of analog systems will use at least op-amp or variant of op-amp. What is variant? There are low noise op-amps, low swing op-amps, high swing op-amps or OTAs, they are all basically op-amps. Okay. So we will see that if I understand my DFAM well and the other two stages, then I have controlled my op-amp design, and if I can do op-amp for requirements like comparator, it is also an op-amp, switch capacitor filter also requires an op-amp. So name any analog system, basic component is op-amp. The biasing of DFAM is we will take care, which is useful for everywhere. So we will also look into biasing circuits using constant current sources, constant current mirrors or constant reference voltages, how to do them. Okay. So these are some things which we are looking for. There is a very interesting method which one gives little interesting thought, and therefore this has been shown. It is called half circuit method. It essentially says that if your system is differential, what does differential definition is? I repeat, what is the differential definition I have? That if one input changes by plus value, the other input must go minus of that by same value. Is that clear? That is called differential system. Is that clear to you? Vn plus delta Vn, Vn2 minus delta Vn. Is that correct? The swing has to be same plus and the other should correspondingly decrease, okay, so that Vn1 minus Vn2 should remain similar. Okay. Now this fact is called differential circuit. Okay. So if you have a differential circuit, okay, which is driven by a constant current source as shown here, and it shows along this vertical line symmetry on left and right, okay, symmetry, the word is symmetry for the two inputs, okay, then we can treat each arm independently, okay, and if we can treat this independently, then it becomes single stage amplifier, okay, and then we can see the net effect together and figure out what is voltage here, what is voltage here, and then subtract, okay, and the ratio of VO1 minus VO2 by V1 minus V2 always can be found. So this is the technique which is called half. So what is the criteria? I said the system has to be differential, biased by a common source, common current source or common bias technique, whichever you do, and it is symmetric for both inputs, then the half circuit method is valid. Is that correct? Is valid. This is only names. For left side is identical to right side as far as the circuit sees. Vn2 Rd2 may be different, but on the right circuit is identical to, you may put values but they are still symmetric. If I mirror of this will come the same. Is that clear? So it is symmetric to the source bias, दोनों साइड के तरफ में वो सेम दिख रहा है, so it is symmetric. Ideal symmetry will be when these are equal and these are also equal, but then that is ISS by 2, so that we already checked into, okay. But we like to see if even if they are not equal, as long as any signal goes higher, the other must correspondingly reduce by same amount at the input, then system will remain symmetric, and we may say this is half circuit method is valid. This is, of course, we have a, this is called half circuit lemma, which is given in a book, maybe if time permitting we will prove today. In that case we say Vp will remain constant for any input combinations, this remains constant, okay. And if this remains constant, Vgs always remains constant for both Vgs1 maybe not be same as Vgs2, but Vgs1 and Vgs2, S is always same potential, okay. If that occurs, all our earlier theory is valid, and therefore we will prove this using this technique that Vp is independent. Please remember, any input combination Vn1 Vn2 essentially still is differential in nature. Change in Vn1 is opposite change in Vn2, that differential part is most important in having half circuit technique valid, okay. If it is not a differential system, this whole concept is not valid. Majority of differential systems will be always differential, okay.
If I want to connect a synchronous system to this differential, what kind of conversion should I do?
If I can always go from single stage or single input stage to a differential converters.
How is that interfacing? Means I am having a front end at single stage, then I am giving a differential stage.
If you see an op-amp, okay, the way it is done is, one of the reference you create independent of that, okay, like you put something else and then outputs are picked up at the both ends, okay.
That means Vn2 I will keep as some other reference and Vn1 only I will keep.
Correct, but that is essentially equivalent saying half here and half here minus. If I have a V, just anyway that will come, if total is something this, I can say half is ascribed plus and minus half is ascribed here, which is difference is same, that this is how automatically it will become difference, okay. Okay, few sheets and then we will stop maybe today. For M1 please have your figure in front of you. I repeat, this figure you should have it because you have on a sheet, so you look at that. Vn1 minus Vp, let us say Vgs is defined as Vs, okay, V1 and V2 sorry. So Vn1 minus Vp is V1, which is nothing but Vgs1, and therefore Vn1 minus Vn is Vp, is that correct? Vgs, this is Vgs which is V1, which is Vn1 minus Vp, is Raj clear? Vn1 minus Vp is Vgs for the transistor, okay. So I say okay, Vn1 minus V1 is Vp. For the second transistor by same argument I say Vn2 minus V2 is Vp. So since both are Vps, Vn1 minus V1 is Vn2 minus V2. Now let us assume that Va is the equilibrium value of V1 and V2, that differential word now coming, and each change by delta V1 and delta V2, delta V1 up this must be equal to minus delta V2 down, is that clear? This is an average value. So if V1 changes like this, V2 must change in opposite sense by same value, okay, opposite sign, essentially saying delta V1 must be equal to minus delta V2. So if I say small signal analysis for this, delta means small signal, change is always equivalent of a small signal. So IDS1 is GM delta 1, IDS2 is GM delta V2, assuming M1 M2 are identical. However, the sum total of this current is always ISS, or GM delta V1 plus GM delta V2 0 for delta ISS is 0, that is no change in the bias current, so these two current must sum to 0, which essentially trying to say that delta V1 is equal to minus delta V2. So if Va is the average, one goes above, the other must go by same amount opposite directions from the average value. So Vn1 plus delta Vn, so Vn2 must go by Vn2 minus delta Vn, that is essentially the feature of differential, that is what I said. So any change in V1, opposite change must come to V2 by same amount, opposite and therefore the signs. Is that okay? Trivials, but that is the concept. Okay. Since we already said that V in 1 minus V1 is V in 2 minus V2, we now define another term V in, as instead of Va for the other side we say now V in is an equilibrium value of V in 1 and V in 2, and if V in changes by delta V in, then V in 1 is V in plus delta V in, and V in 2 will be differential stage, means V in minus delta V in. Okay. Substituting this here, V in plus delta V in minus V1 is equal to V in minus delta V in minus V2. Collect the terms and you get 2 delta V in 1 minus V in 2 is delta V1 minus delta V2, but we already said delta V1 is minus delta V2, or so it is 2 delta V1. So delta Vn is delta V1 or equal to minus delta V2. So change in input is essentially absorbed in delta V1 or delta V2. So Vp still remains constant. So any change is taken care in the Vgs value and not in the Vp value. Is that correct? Delta V1 absorbs change in Vn. Okay. See, average value of Vn1 is, let us say something. So if Vn increases beyond this or goes beyond that, below that, so some value at from where I am assuming, like a DC level plus AC kind of thing. So we say any change in Vn from a given value, it always get absorbed in that V1 V2 values, delta V1 delta V2, and does not affect Vp any time. Is that correct? Because we say it is a differential system, we already said any change, the first earlier one, we say change here is same as change here. That is the definition we gave for differential. Any change here, opposite change must occur the other end, okay. Which essentially telling by maths also that any change in the input is taken care by change in V1 or V2, signs taken care correctly, and it does not therefore any time changes Vp value. Is that correct? And therefore the half circuit concept, which assumes Vp is constant, is valid. Okay. This is only to prove that my statement when I said I am assuming Vp constant, this is only a proof of saying that Vp will always remain constant independent what you do. Based on this, once I now declared that diffam, I can always assume that change in Vn 1 is compensate or opposite change will occur in Vn 2 for a differential stage. In that case, I will now solve a diffam using two separate parts of the symmetry, one left, one right, solve independently outputs and subtract and figure it out whether I get the actual diffam values which people say this is the value. We will solve otherwise also a diffam, okay, other technique which is a more standard technique, but this technique also is valid in diffams. So why did I show you all this? Because this gives you a concept of differential modes, okay, and that is why whole this lemma was proved. What is lemma? Lemma is not a theorem. So what is lemma? Correct. So it is the, already I have used it to prove something, but I assumed it and proved it. That is what lemma decisions are. You assume it to say it is correct, or obviously you assumed it now, so it will be correct, okay. I start with an assumption which I say is correct. Obviously I already started and proved around everything on that, saying oh I came to same point. Yes, you will, okay, but that is what all lemmas and theorems prove. They start with something and at the end prove the same thing which they said. So QED. Okay. So we will stop here.